So we are back to this thing, and let's just do the fourth question now. And so I'll just be doing this non-stop, maybe for 3 hours, who knows. And I'm really tired right now, like this is about the time I should be sleeping. But let's get this done. So the fourth question is photon gas Carnot cycle. So the aim of this problem is to obtain the black body radiation relation. Okay, so this is our aim. We want to obtain this relation, and this is starting from the equation of state. Infinitesimal Carnot cycle, photon gas, whatever. This is a Carnot cycle, and it's infinitesimal. Fine, whatever, we don't really care. So the first thing is express the work done in the above cycle in terms of dV and dP. So it's v2 v plus dV or something similar over there as well, so this shouldn't be hard, right? Just the area under the curve. This is in this case the parallelogram, so it's just height times the breadth, so it's just dP times dV, right? So work done is just dP dV. Yeah, okay. B is express the heat absorbed Q in expanding the gas along an isotherm in terms of P, dV, and an appropriate derivative of E as a function of temperature and volume. Okay, I get it. So these guys are like isotherms, right? Because it's at some temperature T plus dT, and because in a Carnot cycle you have adiabats and isotherms. And so you want to express the heat absorbed in the expanding gas, okay, expanding the gas along an isotherm. Absorbed. So it should be one where your volume is increasing or something, right? So that the work is being done. At the same time, you should also have the energy being increasing, yeah, or something similar to that. Okay. So to me, it seems that going from P plus dP to T plus dt would be would be absorbing work, and in the other guy it would be getting like work. So might be the same case with energy as well. Who knows? And so I'm just gonna guess sort of that in the upper isotherm you are getting heat. You're putting heat into the system because you want to do both positive work and increment in your energy. I assume that. Okay, so then how much is the increment in your energy? So delta E, that's just partial E by partial V at constant temperature times dV. But how much is the work done by the gas in this region? So it's just, well, it's around pressure P, and it's going for at least dV thing, so that's the thing. So the heat is just the addition of these two, right? So this is the work done by the gas, by the way. Yeah, and so just have this as the work, as the heat input, right? I'm just actually gonna write this as an input because I'm assuming they're gonna do some Carnot stuff, but whatever. Okay, C is using the efficiency of the Carnot cycle, relate the above expression for W and Q to T and dt. Oh, right. Okay. So the work upon Q and thing is just the efficiency. So in this case, it's just dP upon P plus, I'm just going to call this E sub V at constant temperature, whatever. And this thing, we know it, since it's a Carnot cycle, this is going to be just 1 minus T cold. The colder one is small t upon T hot, so T plus dt. Yes, and that's just equal to dt upon approximately T, I would say. So this is the equation that we want to be dealing with. All right, so what does this tell us? That tells us dP upon dt is equal to, or more like T times of that, that's equal to P plus E sub V at constant temperature. Okay, so use this information. Wait, what are you supposed to do? Yeah, so use the efficiency of Carnot cycle and relate the above expression. So that's done. This is the part with C. Now D is observations indicate that the pressure of the photonic for the photon gas is given by P equal to A T power 4. right, where A is this, okay, it's a constant. Use this information to obtain E as a function of temperature and volume. Assuming E of T comma 0 is 0, so that's when volume is 0. Okay. Oh, okay, so we could probably solve this equation, I guess. So since now you know that P is what, right, as a function of temperature, we can just write this as A, actually, 4A T power 4 is equal to A T power 4 plus E sub V at constant temperature. And so just get partial E by partial V at constant temperature being equal to 3A T power 4. And I guess this implies that energy is just 3AV T power 4 plus some function of temperature, as I assume, because we integrated with respect to the volume. Yeah. Okay, and we know by extensivity this has to be having an n over there or something. Fine. So using the efficiency, what was I doing? This is the question D, right? Okay. So use this information to obtain energy, assuming that at volume equal to 0, energy is 0. Okay. So put volume equal to 0. What you would get is like f of t is 0. Okay, cool. Okay. That just means this equation. So you have the energy, basically. Cool. Fine. So find the relation describing the adiabatic. So we're going to go get entropy as well, right? Fine. I think it shouldn't be that hard because you have this equation that ds upon de at constant volume is equal to the 1 upon temperature thing. So I guess you could write this as ds upon dt at constant volume is equal to 1 upon tde upon dt at constant volume. But then we know how to compute this, so that's probably gonna give us some good thing. So we just get 1 upon t and then the derivative of this stuff. So it's just 12 AVT power 3, right? So that's just 12 AVT power 2. That's what ds upon dt is. And so now we just integrate, right? And so you get entropy as 4 AVT cubed, right, plus some function of the volume, because we integrated with respect to the temperature. Okay, cool. Oh, but then we can apply the third law and say that at temperature equal to 0, entropy should be 0. So that essentially means that this function should not exist. So you just have this, in fact. So you got the entropy. Cool. Because I mean this was the last question anyway, so that probably has to happen. And so now we want to find the relation describing the adiabatic paths in the Bow cycle. So if s is constant, what should happen is that this quantity should be constant, but we want a relation between p and v. So you know that p is just a t power 4, right? Yeah, so just t is what? T is like p upon a to the power of 1 upon 4, something like that. So what should happen is we'll put that in there, and so you'll just get v times e power 1 by 4. That's some sort of a constant, right? Yeah, or more like pv power 4 is constant. That's better. So that implies ds equal to 0 implies pv power 4 is constant. Cool. Next question. So the second question, or the fifth question, is consider two substances, temperatures T1, so just two substances, T1 0, T2 0, coming to equilibrium at final temperature Tf. So something happened and now they're coming to final temperature Tf through heat exchange, so they can exchange heat. Fine. By relating the direction of heat flow to temperature difference. Direction of heat flow to temperature difference. So you are saying that wherever you have hot to cold, that's where the heat flows. Show that the change in the total entropy, which can be written as this quantity. So you have delta S is equal to delta S1 plus delta S2. So that's the entropy change of this guy plus this guy. That's bigger than or equal to. So, you know, the usual entropy equation. Yeah, I mean, this inequality actually makes sense. And then you can write this as, yeah, because the dq thing is actually just inverse, because, yeah, right. So there's nothing about work or anything. through heat exchange. So there's nothing else happening. Fine, cool. um, right, this is an example of the more general, and in fact even if there is work we don't really care actually, because the heat transfer is supposed to be the same. Yeah, so this is a more example of a more general condition that in a closed system equilibrium is characterized by the maximum value of the entropy. Okay, but we're not caring about that, right? I mean, it's an example of the more general condition. We don't want to be deriving the general condition. So now consider a gas with adjustable volume and diathermic walls. So shouldn't we first of all be like finding what this TF thing is going to be? I guess so. Anything about the heats given? Nothing really. Yeah. Fine. Okay. Now consider a gas with adjustable volume V and diathermal wall embedded in a heat bath of constant. So I'm just gonna draw that out. So a gas with adjustable volume V, diathermal walls. So this is letting heat flow, embedded in a heat bath of constant temperature T. So it's connected to something that has a constant temperature and a fixed pressure P. So the pressure is fixed. Some piston, I don't know. All right, and it's volume V. The change in the entropy of the bath is given by delta S. Bath is just delta Q bath upon temperature, which is just delta Q gas upon temperature is equal to, yes, that's completely correct. What's wrong with that? So the P delta V of gas. So delta Q gas is delta E gas plus P delta V gas. Yes, because P delta V is the work done, and yes, so we can certainly do that. The heat given to the gas is just Q gas. So you can certainly write this. Yeah. Right, so minus P delta V is the work done on the gas by the atmosphere. Fine. By considering the change in entropy of the combined system, established that the equilibrium of a gas at fixed. Wait, so what are we supposed to do in. Oh, this is part B. Wait, what are we supposed to do in part A though? Oh, so we are supposed to show that the change in total entropy, which can be written as delta S, fine, that must be positive. Ah, sorry. I mean, that's actually trivial. I kind of don't want to be showing this, obviously. But essentially, the thing is you're doing dq times 1 upon t1 minus 1 upon, or, well, just, okay, do that thing. So just 1 upon t1, t2, and then you got t1 minus t2. Where, so this is the new 1 upon t2 over there, cool. Where your heat is, so heat element dq is flowing from t2 to t1. And this will be positive only if t2 is bigger than t1, right? Yeah, so I'm just going to assume without loss of generality that t2 is bigger than t1 at all instances while this is happening. And so yeah, this just keeps on happening until you get like some constant temperature, and then it doesn't happen anymore. I mean, as soon as they're at the equal temperatures, this does not happen anymore. And so yeah, this must be positive. I don't know what is to show over here. Like, it just is, because t1 is bigger than t2. Come on. Sorry, I mean, yeah, actually, right? t1 is bigger than t2. Yeah, okay, it should be t1 bigger than t2, sorry. Because heat is flowing to t2, right? So t2 has to be the smaller one. Cool. So yeah, as long as t1 is bigger than t2, we sort of have assumed that heat will flow from hot to cold, right? That's what they're telling us to do. And so using that, it's easy to show that this quantity is positive. So I don't know what is there to show about it. I'm just gonna move on. The second part is, okay, so you have all of that stuff. By considering the change in the entropy of the combined system, established that the equilibrium of a gas at fixed temperature and pressure is characterized by the meaning of the Gibbs free energy. G is E plus P PV minus TS, right? So what is dg, so delta G though? That is equal to delta E plus In this case, pressure is constant, so just say P delta V. And then temperature is constant, just minus P delta S. So delta S is for the gas, right? Yeah. We kind of don't know what T delta S for gas is because this could be completely irreversible sort of a thing. We have no idea. But we do know that the delta S bath is exactly just this quantity, right? More like negative 1 upon T the bath is actually this quantity. So we can just write it like that. Negative T delta S bath, negative T delta S of the gas. That's what delta G is. So it's just negative T delta S universe. Alright, so what we want to say is that the equilibrium of a gas is characterized by the minimum of the Gibbs free energy. Cool. So it has to be at the minimum, our Gibbs energy has to be at minimum, because if it is not and there exists something, so this is like Gibbs energy and this is some variable x, I don't know, maybe the volume, who knows, and so there is some state which has a lower Gibbs energy, then the transition from this to that guy has a delta S, which is, so the delta G would obviously be like negative in that case because lower Gibbs energy for this transition. So then the delta S universe would be positive. And so that means if our system somehow takes this transition, it can never go back because the second law, right? And so this doesn't make sense. Like, why would this not have happened after infinitely long amount of time? And equilibrium is for infinitely long amount of time. And so that implies that, yeah, your state at equilibrium, that must be at the minimum Gibbs energy. It can't be at anything above a certain value. I mean, it can't have any Gibbs energy for some other state below it. So that's the thing. Cool. Next, constant heat capacities. Given two bodies with temperature independent heat capacity C1 and C2, important to note, temperature independent heat capacities, and initial temperatures T1 bigger than T2. So you're measuring two bodies, one is at temperature T1, another is at T2. This has heat capacity C1, this has heat capacity C2. If the two bodies are brought into contact such that the only heat exchange is between them, right, so that is to say no other heat exchange is happening, or only heat exchange is between them, what is the final temperature and what is the change in entropy? All right, so the final temperature is probably not that hard to calculate, I think so. So we can just use the work energy theorem and all that stuff. There is no work in the first place, so just like a conservation of energy, more or less, I guess. Yeah, so you have been given the heat capacities, so temperature independence, like, doesn't matter what temperature of this guy is. So this just means like C delta T1 plus C delta T2, that should be equal to 0, right? Because the total number of, so total energy is conserved essentially, right? And so what does this mean? So this just means C times Tf minus T1 plus C, so C1 actually, C2 times Tf minus T2, that's equal to 0, and that implies Tf is just C1 T1 plus C2 T2, that upon C1 plus C2. Cool. That is to say, whichever has a bigger heat capacity is the one which sort of affects the temperature more. Anyway, so that's part A. Okay, we also want to find the change in entropy. So that's sort of more subtle, I suppose. So we'll have to integrate. So integrate dq upon temperature T 1. So just you know that, let's just assume that T2 is bigger than T1, right? So just have dq upon T1 and minus dq upon T2, where dq is the heat element flowing at a particular time. And so let's just think of dq being, so q being, which is the amount of heat that has flown till now, being a function of the temperature, right? Of the temperature of, let's just say, the first guy. So the T1 thing is going from a T1 to, so let's just say this guy has a variable temperature T throughout the process. So just have T1 to Tf essentially, right? Or let's just say T1 naught. T1 naught is better. Cool. So now you can figure out what T2 should be, right? Yeah. So at any given instance, if the amount of heat that has flown is Q, then what should happen? Then you just have q is also just the change in, it's related to change in this guy, so just c times of t1 minus t1 naught. Cool. But at the same time you also have q is c2 of t2 naught minus t2, right? Yeah. And so in that particular way you can relate um, you can relate t2 and q both to t1, right? Cool. And so differentiating this thing, just have dq is equal to c1 dt1, right? That's one important bit. And taking a ratio of this whole stuff, what you have is that c1 upon c2 t1 minus t naught, t1 naught, sorry, upon t2 naught minus t2 that's equal to 0, sorry, it's equal to 1. What that gives us is, well, some value for t2 obviously, so t2 naught minus t2 is equal to c1 upon c2 times t1 minus, this is kind of unnecessary, isn't it? It sort of is. Wait a second, if you kind of think about it, you don't even have to be converting everything to one variable, right? No, you don't. You actually don't, because you can split this into two different path integrals, and both of, like, yeah, it's gonna have the same value though, it doesn't really change that. Right, so just get the entropy changes for each of them separately. That's something we could have done already, but yeah, so essentially just have, or you could just have plus dq and all that stuff, but whatever. And so just have dq equal to c dt1 in this thing, so just have integration of c1 dt1 upon t1, but it's going from t1 till t final. But then over here you have minus integration of, so the dq thing is negative now, so it's like, because the temperature is decreasing, so just plus c2 dt2 upon t2, but now temperature is going to go from t2 to tf. Cool. That is the total entropy change that you are going to suffer through. So essentially just have c1 delta t1 square, so just tf squared minus t1 square upon 2 plus c2 tf square minus t2 square upon 2. That's the thing, right? So it just gives us c1 plus c2 upon 2 times, or just take that 1 upon 2 common, whatever, just 1 upon 2, and then you got c1 tf square plus c2 t. That's the equation. Just move on. Just write in c1 plus c2 instead, it's better. So c1 plus c2 tf square, and the reason is because tf was basically just c1 t1 plus c2 t2, right? So you can convert this, and now it will just be this quantity c1 t1 plus c2 t2 squared upon c1 plus c2 basically. And I guess we can sort of expand this, so just get c1 square t2 square plus c2 square t2 square plus 2 c1 c2 t2 t1, whatever. This whole thing is like upon, yeah, whatever, we'll deal with that later. Sorry. So minus c1 square t1 square minus c2 square t2 square in the cross terms, so just minus c1 c2 t1 square minus c1 c2 t2 square. So some stuff just cancels, it should be 1 over there. So you just have this remaining, so you can take that c1 c2 out, and also the negative sign out, so just negative 1. What the hell, why is this a negative sign? Yeah, okay, something is wrong. This shouldn't be having a negative sign, right? Temperature T1. Yeah. Stay true to that. What the hell? No. No, something is wrong, isn't it? I did something incorrectly. I can sense it. Yeah, I certainly did something really incorrectly. It should be natural log. Why is there a square? So just C1 natural log of Tf upon T1 plus C2 natural log of Tf upon T2. That's how it should have been, right? And now we can't sort of simplify this any further. Well, that sucks, but whatever. Uh, can be actually. I don't think so. I'm just gonna leave it like that. So that's the A part, that just have delta S is this quantity. Next, B is what is the final temperature if the Carnot engine is used to transfer heat between the two bodies? What is the amount of work done by the engine in this case? Final temperature of the Carnot engine used to transfer heat between the two bodies. Okay, I get it. Right. So now the heat transfers are not exactly the same. There's some work that's being done. So you have this body, this gets dq1. You have this body, this gets, or I should say you're taking away negative dq2 from this, right? And you're converting it to work, obviously. There's some efficiency and stuff going on. So now it's sort of essential that you do write everything as a single temperature. This is gonna be hard and pretty long. What is the amount of work done? Okay, let's just do this. Let's just start integrating. Yeah. So we'll assume that the colder body has a temperature capital T at any given time, and this has some temperature. For now, let's just call this T dash. And let's just write everything in terms of the taken sorry, or more like the heat given to this body. No, let's just say heat taken from this body, right, till now. So what do you have? You have that the amount of heat given to this body will be precisely just will just be T upon T dash of Q. Actually, I think the heat given in Q would be better. So then the heat taken would just be T dash upon T times Q, right? That sort of makes sense. So then it's like reversible and all that stuff. We'll think about the work later. Right now this is the scenario, and so now what you have that dt, more like C1 dt, that's equal to dq, and C2 dt dash, or more like the negative of that, in fact, that's equal to T dash upon T times Q. You can't kind of figure out what T dash is going to be, right? Yeah, that's a problem. You want to be writing T dash as a function of most probably the heat. I mean, yes, everything is just a function of a single variable, but now how do I start to write this down? That should be a dq over there. I suppose the way that we would do this is just, well, divide. So you just get C1 upon C2. Yeah, right, that's probably a good idea. Oh, who am I kidding? I write everything as a function of dt, right? That's the way to go. So instead of dq, we'll just say, well, C1 dt. Right, cool. So now what is the final temperature, essentially? So you have this equation. This tells you how the temperature T dash changes as the temperature T changes. That's probably going to be useful. Let's just have dt dash upon T dash. Okay, let's actually not get too ahead of ourselves. Let's not delete this thing. We'll come back to this later, but first we need to figure out this stuff. Right, so we just have dt dash upon T times C2 plus C1 dt upon T, that's equal to 0, right? That's kind of obvious. So we just integrate this thing, right? so it should be t dash over there. Just get like c2 natural log t dash, well, just like some final temperature, right? So just tf plus c1 natural log of tf, that's equal to c2 natural log of t2 plus c1 natural log of t1. That gives us a thing. So just have natural log of tf equal to this stuff. So it's a sort of a GM, if that makes sense. Like it's just tf is equal to c2 power, sorry, t2 power c2, t1 power c1, all of that to the power of 1 upon c1 plus c2. Right, so that solves the b part first. You just have the t final is this bizarre quantity. Okay, now we want to figure out the delta S for the universe, obviously. I mean, okay, that's actually 0. We don't even need to do anything. What is the amount of work done, right? Okay, so we need to find the total amount of heat that we have put to the thing, okay, obviously. So how do we do that? Well, one thing is we integrate our dq guy, so just integration of dq is just c1 dt from t1 to t final. That's the amount of heat that you have put into the colder body, and you subtract this from the amount of heat that you have taken from the hotter body, which is just integration of, so that's just c dt dash, so it's this quantity, and so it's just t dash upon t c1 dt, right? Yes, I assume that's correct. Yeah, and this is from, once again, t1 to tf, right? Now we need to find t dash. Yeah, we need to express t dash as a function of temperature T, but how? Well, probably like this. We just have tf power c2 plus so we just have tf power c2 and, sorry, we have t dash power c2 and t1, so okay, it's just t power c1. That's a constant, sort of, so we can set it to be equal to t2 power c2 and t1 power c1, right? And in that way we have t dash is just equal to t2 times t1 upon t to the power of c1 upon c2. That's one good thing. So yeah, we can use this. Now we don't need all of this stuff anymore. This is the main equation, sort of. You just plug that in, what do you get? So just get, integration, so t2 out, so just like figure out what this integral is. So just t2, heck, what was I gonna say, t2, then you have this upon t, right? So actually it's supposed to be t2 and then t1 power c1 upon c2, integration of t power -1 negative c1 upon c2 dt. Okay, this times of c1 as well. Okay, fine, just that. It's negative t2 t1 c1 power c1. Come on, ink. Divide this by that stuff. So it's just supposed to be times of c2 upon c1. So this just becomes c2 essentially. And now this thing is t power minus c1 upon c2, and it's going from, well, this is going from t1 to t2. Cool. So at t1 and that is at t2, so we can just use that to switch this up. So it's gonna go from, oh sorry, it's final, right? Yeah, it's gonna go from t1 to t final. Now it's like t final t1, whatever. So at t1 this quantity just gives us like t2 c2 minus, when you put t final over there, you just get t2, so okay, c2 over there, so t2 c2, and then t1 upon t final to the power of c1 upon c2. Amazing. That's what this integral is. What about the other integral? So just have this quantity minus minus this is just, well, t, so just c1 tf plus c1 t1, sort of. Yeah, I guess that's right. That's certainly right. So now we can use what tf is, most likely. Yeah, you can plug that in. Okay, I see. There's gonna be some stuff happening. I get it. So you can actually bring that c1 inside, isn't that right? Whatever. So what do you have? tf is just this quantity. Plug that in. So just have t1 power c1 plus c2, and some stuff cancels. So just get t1 power c2 upon tf upon t2 power c2, right? The power of c1 upon c2 times c1 plus c2. So this cancels with this stuff. Let's just get this. I suppose you can bring the t2 inside, right? Yeah. And so you can bring the t2 inside, so just get, well, c2, and then you got t2 power c1 plus c2, and then t1 power c1 upon t2 power c1. That is 1 upon c1 plus c2. Cool. Guess what that whole thing is? Yeah, we've seen this somewhere, haven't we? It's just the tf value. So this is exactly just tf, which sort of makes sense. I think so, personally. Yeah, so he's just saying that t2 times t1 upon tf to the power, because this was also a relation, right? Yeah. Yes, and it certainly makes sense to me. So just c2 tf, essentially, this whole thing. Cool. Why do I feel I'm making some stupid mistake? Obviously, because I could have done this directly. I didn't need to integrate. Yeah, that whole thing was just stupid. I could have done this directly. Whatever. Just shows that it works out. Just have c2 times t2 minus tf minus c1 times tf minus t1. That's the quantity that you're interested in. Let's just leave it at that. So this thing is the work done. Alright, let's go to the next question. 7th, non-Carnot engine. Consider engine that operates between a set of temperatures. T max is so at different temperatures, so it's like at T1, T2, so on till Tn. Tn is the minimum. Fine, this is the T maximum, and this thing is T minimum. For a subset of these temperatures, T alpha plus, the engine takes in heat Q alpha plus. So for each T alpha, you have Q alpha, whatever. While the remaining temperatures T beta, the heat, fine. The engine does a net work is equal to Q plus minus Q minus. So Q plus is defined as the summation of all the ones where you take in heat. Yeah, right. And otherwise, okay, so Q minus is just where you give heat. So that is, if this efficiency is less than that of a Carnot engine operating between T max and T minimum. So this engine is what again? Just some random engine. Cool. Yeah, right. So the delta S thing is basically just takes in heat, gives heat. Cool. The efficiency is just the work done upon that. Whatever. So what's the delta S thing? The delta S is just minus, so just minus Q, let's say summations, minus summation of Q alpha upon T alpha, right? Because taking heat from that, plus the summation of Q, what is it, beta upon T beta, and then the work done is just this quantity. It's just a summation of Q alpha minus Q beta, right? Cool. Right, okay, I think I'm getting the hang of what's going on. So this upon the, so the efficiency is just this upon okay, so the q plus scenario, which is just summation of q alpha, right? Okay, so we just have to show that this thing is less than 1 minus t minimum upon t maximum, essentially. So like Tn upon T1, right? Yeah, which is to say that we just have to show that summation of q beta, this should be q, sorry, upon summation of q alpha, that is bigger than Tn upon T1. Yeah, right, that's what we want to show. And how does this happen? Well, we show that delta S, well, that's obviously has to be bigger than 0, and that implies that summation of q alpha upon, so that's like summation of q beta upon, sorry, q, yeah, so q beta upon t beta is bigger than summation of q alpha upon t alpha. But you know, as a matter of fact, that each t alpha is less than or equal to wait, yeah, right, so it's less than or equal to t1, right? So this is it's bigger because they're dividing by a smaller number now, right? It's bigger than summation of q alpha, all of that, upon t1 every single time, and similarly this is less than summation of q beta upon tn, and that's kind of what we wanted to prove. So this was like a bit too easy for me. I don't know why this question is there, but yeah, that's what we wanted to prove, and we're done. So this question was anyway, next question. It's an optional question, fine. So the solar system originated from a dilute gas of particles sufficiently separated. Solar system, I'm okay, we're studying thermodynamics and now we're suddenly going to solar system. But anyway, just read on. So it's originated from a dilute gas of particles sufficiently separated from other such clouds to be regarded as an isolated system. Under the action of gravity, the particles coalesced to form the sun and the planets. So now the motion and organization of planets is much more ordered than the original dust cloud. Why does this not violate the second law of thermodynamics? Or because you gave away some energy. So if this is your solar system, you have some like cloud or whatever of dust, and then because of gravity, this gave you like the sun, the different planets, whatever. What you are not considering is that this process is highly exothermic. Like, you had a lot of energy leaving this solar system in the form of light, so photons, right? And yeah, so there's just energy leaving, but essentially it's like heat, right? It's like heat leaving your yeah, so you should probably also consider that, right? I mean, yeah, the medium is not through the, what is it called, the motion of your particles or whatever, but still heat is leaving your system, and so you should probably consider that. Or if you don't want to consider that, consider these particles to be part of your system. It's an important thing. And in that case you could say, oh well, no energy is leaving. Okay, cool. And in that case, yeah, the entropy is increasing because these particles are so many in number and they like are all scattered and everywhere. So we can certainly say that the entropy is increasing. Okay, so yeah, it does not violate the second law of thermodynamics. Next, the nuclear process of the sun converts protons to heavier elements such as the carbon. Does this further organization lead to reduction in entropy? This is maybe, I think so. Wait, from two atoms, if you have one atom, then it's probably better, right? But then you also have to probably consider the kinetic energy and those motion things, and yeah, I don't know. But for me, it looks like, yeah, this is probably better. I think so. Yeah, I think it's reducing the entropy further. So I think B is a yes. Fine. Next, the evolution of life and intelligence requires even further level of organization. How is this achieved on Earth without violating the second law? Once again, the same thing. You're radiating heat away all the time. So you can't say that that just entropy is decreasing. That's not the thing. What you should say, so that the second law would be violated, is that the entropy of universe is decreasing, which it is not. So you are not saying that the second law is being violated. And so yeah, this was more of a philosophical question than you know than what I thought we would have, but whatever. I think that's it. So this is like the 8 questions that I wanted to do. I'll see you guys in the next video. Bye.